Hello. So we now start on lecture number 4 of the series on tectonics and geodynamics. In the last lecture, we talked about the topography of the seafloor. Now we will begin to talk about seafloor spreading, right? It's a phenomenon that is unique to the seafloor itself. Now, the seafloor, the concepts that we will cover in this particular lecture will deal primarily with seafloor spreading and what we call seafloor magnetic anomalies. These are the two major things that we will discuss in this particular lecture, and these really form the basis of the beginnings of this theory that I've already mentioned, the plate tectonic theory, right? It really was the starting point from which people began to talk about plate tectonic theory. Now, this theory of plate tectonics, it had evolved as a consequence of the findings of many people. However, the major players in the system, there were others also apart from the ones I've mentioned here, but they include some people who we've discussed already. That is Alfred Wegener, among the most prominent. He talked about continental drift, which we now realize is one of the prominent manifestations of plate tectonic theory. But there were also others like Harry Hess, who talked about what we call seafloor spreading. Two people called Frederick Vine and Drummond Matthews discovered magnetic anomalies on the seafloor. Then we come to a Canadian geologist by the name of John Tuzo Wilson. He first evolved the concept or proposed the concept of rigid plates. And Dan Mackenzie, who then talked about how plates would move on a spherical earth and the stabilization of triple junctions, points with three plates meet. So all of these are things that we will discuss as we go further into this lecture and into the next. So let's begin then with one of the second pioneer. We talked about Alfred Wegener before in lecture 2. We'll now talk about Harry Hess. Now, Harry Hess was a very interesting person. He actually was a person who studied geology at Yale University, and most interestingly, and maybe it would be an inspiration and give hope to some of you, that he actually failed his first course in mineralogy at Yale University. So he was told by his teacher that he had no future in the subject. However, by the end of the 1930s, right, before the Second World War began, Harry Hess was already teaching geology, and he was at one of the most famous universities in the world, Princeton. So he was teaching geology at Princeton University when the Second World War broke out. Now, at the time of the war, he actually supported the war effort by becoming a part of the US Army. And during that time, he actually collected a lot of sonar data from the ocean floor. He was actually in the US Navy. And at that time, he discovered these things called guyos. Now, guyos are also topographic features that you see. Let's get this here. So, guyos, these guyos are also topographic features on the ocean floor. Now, these are, if you take a flat ocean floor like this, and let's say this is mean sea level, so let's say this is mean sea level, then guyos would be around here. So these are really flat topped peaks. Now, these are volcanic in nature, and these little mounds, actually, these are absolutely flat topped, as if somebody has chopped away the top of a mountain. Now, indeed, that is the case. We now realize that is the case, but this was actually the first person who discovered this was actually Harry Hess, and he did this while working with the US Navy in the Second World War when he was looking through a lot of this sonar data. He was also a person who confirmed, right, the existence of mid-oceanic ridges and ocean trenches, right, both after Marie Tharp and Johnston had actually proposed that they existed. So he collected all the information that he had, proved that these things also existed, and then you had these guyos also existing on the ocean floor. These were flat-topped volcanic peaks that existed in parts of the ocean. So Harry Hess, right, with this very interesting background, when he was working, he noticed things. Now, one of the jobs of a natural scientist, right, like us, like Harry Hess, was actually to notice things that were abnormal. And one of the first things that he noticed is that, of all the fossils that are found on the continents, right, we can find fossils that are around close to 500 million years old. However, the oldest fossil collected from the ocean floor was only 180 million years. Right? So, this is just 180 million years. So, the oldest fossil on the ocean floor was hundreds of millions of years younger than the oldest fossils that were found on the continents. Now, the continental crust is almost 4 billion years old. So, therefore, I mean there was a drastic difference, right, between the age estimated for the oldest ocean floor, estimated from the fossil, and age that we had for the oldest ocean continental crust that we could see. There was another problem, of course. In a place which was standing below a body of water, right, there is a particular rate at which sediments are expected to precipitate. Now, we knew this because we knew that the oceans of today, we know that the rivers are actually draining a lot of their sediments into the oceans. There are materials which is periodically dislodged from the continental shelves into the abyssal depth. So, if you consider this to have happened, right, over 4 billion years, then you should get a very substantial thickness of sedimentary rocks or sediments on the ocean floor. And that was by no means the case. If you consider the actual thickness of sediments, which is about 1 to 2 kilometers really on the even an old ocean floor, that is very, very meager, right, if you think of the oceans being 4 billion years old. So, these were two things that really intrigued Harry Hess. And what he thought then is that it would probably be best if you could perhaps explain these observations if you assumed that there was ocean floor that was relatively new, and maybe this was actually created by magma rising out of the mid-oceanic ridges. Now, as we have discussed in the last lecture, this wasn't completely original. The first person who had actually suggested this might have happened, right, was actually Arthur Holmes way back in the early 1940s. But even after that, Marie Tharp actually, when she detected the mid-oceanic ridges, she actually had proposed that probably this moving aside, these earthquakes, these rifts that she observed at the top of the mid-oceanic ridges, these might have been caused by magma which was rising, material rising from below. She didn't specifically say it was magma, it was material rising from below that was actually pushing the MOR. So, Harry Hess sort of revived that idea. And he thought actually that there was magma rising from the mid-oceanic ridges, and by that time people knew there were volcanoes which were linked to the mid-oceanic ridges. We saw that there were volcanoes linked to the mid-oceanic ridges in the last figure of the last lecture. So, the question was, all of this together meant what Harry Hess was suggesting is that you had new ocean floor being actually created over time at the mid-oceanic ridges. So, what was happening is that new magma was coming out, solidifying, erupting onto the surface of the earth, forming lava, solidifying below water, and then it was moving apart, right. It was rifting because the sea floor, he said, was spreading. So, this was his whole idea, that the sea floor was spreading. Now, let us just think of what this means. If the sea floor spreads, that means that the earth might be expanding over time. Now, it's not as absurd as this sounds now, because at that time the expanding earth hypothesis was also something that was being considered, and it had been a theory for some time that the earth was actually growing with time. How it was growing was not actually thought of too deeply, but people did suspect that there was some expansion of the earth with time. The problem, of course, is that there was no astrophysical evidence for the earth's surface area increasing. Now, what kind of evidence? Why should astrophysics provide us with any kind of evidence about the earth's surface area? Well, it's easy to think of this if you know that the earth is approximately a sphere, right. So, if the earth is a sphere, then its surface area would be 4 pi r square. So, if the earth is actually expanding, right, and if the surface area has to increase, 4 pi r square should be a bigger value with time. Now, in 4 pi and r square, obviously you can't increase 4, you can't increase pi. The only thing you can increase is r square, or r. If you increase r square is going to increase. So, the radius of the earth may increase with time. But if the radius of the earth increases, that means that the volume of the earth, right, 4 upon 3 pi r cubed, right, that should also be increasing. And if the volume of the Earth increases, it has implications for the density of the Earth, it has implications for the mass of the Earth. So, if you now consider, right, what was happening over time, it is very easy from astronomical and astrophysical evidence to actually detect whether this was happening. And it was very clear that at least for the past 4 billion years, there is no evidence to support that the Earth has been expanding with time. There is no evidence to say that. So, if the seafloor was spreading over time, right, then it meant that it implied that that the Earth's surface area was expanding, but Hess thought that he had a way out. And to do that, he recalled an old evidence or scientific evidence that was known, right, since the 1920s to 1930s. And this is something we've talked about before. You remember that Venning-Menez, right, a geophysicist, he had actually said that the Earth's trenches, the ocean trenches which he'd identified, right, which had been identified by Johnston, these were areas associated with negative gravity anomalies. That is, there was a mass deficiency in these parts, which meant that the crust itself was actually subducting into the Earth. So, that means there was a mass deficit in those parts of the trenches. So, these were areas, he said that these were locales of downwelling of the Earth's crust. And this is what Harry Hess invoked back. He said that new ocean floor was actually created by magma that was rising at the MOR, and then this ocean floor was consumed at the ocean trenches. Now, if the ocean floor was created at the ridges, consumed at the trenches, it meant that ocean floor could never become as old as the continents. That would explain why the ocean floors were never that old, right? Why the oldest fossil was only about 180 billion years. It would also explain why the sediment thickness on the oceans is not that high. So, in all then, Harry Hess's theory, right, was that you had a very dynamic seafloor which was spreading out at the mid-oceanic ridges and being consumed at the trenches. And he called it, or this became known as the seafloor spreading hypothesis, and he published this in his very famous paper, The History of the Ocean Basins, in 1962. Now, this was a marvelous little theory, and if you think of how it would, if you think of this pictorially, you can visualize this as this being the core of the Earth, then you have the mantle of the Earth. At that time, people supposed that the mantle was the hot part which was probably convecting, as a result of which you had this upwelling convection currents bringing up the mid-oceanic ridges where you would create a rift valley, because of which you would have these, tensional stresses which would actually pull apart the ocean floor here. So, the crust would split and then the crust would go down, creating a depression at the trench. So, you can see the depressions being created at the trench here just because the crust was going down. So, this was broadly Hess's idea, right, at the time that he proposed his model. This is what he thought would be the case. Now, the problem of course was what was the proof? He had proposed a theory, right. It did sound logical, but he really had no proof. So, how could you actually prove that seafloor spreading had taken place? And the proof of the theory came from really something completely unexpected. It was an extraordinary source. It was actually from the magnetic field of the Earth, and it was also from this rock called basalt. Now, basalt, to all of you who have studied geology before, you know that basalt is actually the most common type of rock on the Earth's surface. It was 50% of the lava that extrudes onto the surface of the continents is basalts. In the oceans, it's many times more. So, really, it is really the most common type of igneous rock on the Earth's surface. Now, why is it so common? We know now the mantle of the Earth, which is made up of a rock called peridotite, when that mantle melts, when this mantle melts, it produces a liquid that solidifies on the Earth's surface, and this liquid, when it solidifies on the Earth's surface, it forms basalt. So, basalt really is formed whenever the mantle melts. So, when the mantle melts, the liquid that is produced, right, it rises to the top. When it erupts onto the Earth's surface, right, it forms this rock called basalt. It solidifies to form basalt. Now, when it erupts, a basalt has a temperature of around 1100 degrees centigrade, and the first mineral that invariably crystallizes from a basalt is a mineral called olivine. Now, after olivine, the most common mineral that crystallizes is either plagioclase or clinopyroxene, but in between, at some time in between or sometimes just after plagioclase crystallization, in much smaller quantities, this very important mineral magnetite begins to crystallize from the magma on Earth. So, as lava cools, magnetite now begins to crystallize. Now, this is magnetite. When it crystallizes, the temperatures are very high, it's around 1000 degrees centigrade. However, as a basalt solidifies, right, the magnetite which is crystallized from it, right, also has solidified and it begins to cool and ultimately cools below what is the Curie temperature of magnetite. Now, this is round about 580 degrees centigrade. Now, the Curie temperature is the temperature below which a which is magnetic in nature can preserve magnetism. So, if you increase the temperature of a magnetic material above its own Curie temperature, it will stop being magnetic, it will lose its magnetism. So, the Curie temperature is the other way around. Now, you had a very hot magnetite crystal. So, once it cools below the Curie temperature, it becomes magnetized. Now, how would it become magnetized? Because it lies within the Earth's magnetic field. Now, the Earth's magnetic field is something that the Chinese told us around 1000 AD. So, from that time, the Chinese knew that the Earth had a magnetic field and it was roughly like a dipole, like a bar magnet passing through the center of the Earth. So, and from that time itself, we knew that the Earth had a magnetic field. And although it's quite weak, so when this magnetite crystallizes and it cools below its Curie temperature, right, the magnetic moments of the magnetite grains, that is its axis, it becomes parallel to the Earth's prevailing field at the time. So, whenever it crystallizes, whatever is the Earth's field, right, the magnetite becomes aligned in accordance with that field. Now, as the rock cools further, it cools below something called the blocking temperature, which means that once you cool the rock below its blocking temperature, you can't change the way it's magnetized anymore. Right? So, the Curie temperature is the temperature above which a magnetic substance would lose its magnetic property. The blocking temperature is the temperature below which it will actually retain its magnetism unless you damage it in some other way. Now, the blocking temperature is tens of degrees below its Curie temperature. So, it means that even if the magnetic field of the Earth changes subsequently, the rock will tend to preserve whatever was its magnetization at the time that it formed. So, this is called thermoremanent magnetization. It's something that we will talk about in lectures subsequently. Now, we know though that a basalt, when it crystallizes, the magnetite that crystallizes from a basalt makes the basalt magnetic in nature. So, it will have a magnetic polarity. In the early years of the 20th century then, a person called Bernhard Brunhe, he was the director of a geophysical laboratory in France. Now, he actually was studying the magnetization of samples from a basaltic lava flow, which was actually overlying some argillaceous, that is silty sediments, right, in a particular part of France. It was in the volcanic district. So, you had a basalt lava flow, and underlying the basalt lava flow you had these sediments. So, these sediments were actually baked, they were metamorphosed, they underwent contact metamorphism. So, now when he actually looked at these basalts, this is as way back as 1905, when he actually looked at these basalt flows and the underlying sediments, he observed then that they were both magnetized, and they were magnetized in a direction and an axis. The axis of magnetization was exactly opposite to that of the present day field of the Earth. That is, if a basalt erupts today, it will have a particular polarity. So, when it crystallized, what Brunhe observed was that these lava flows that he observed in this part of France, they were magnetized in exactly the opposite way, as if the Earth's present day North Pole was the South Pole and the South Pole was the North Pole. Now, he in fact correctly interpreted this observation as a consequence of an inversion of the Earth's magnetic field. He thought that the Earth's magnetic field must have inverted in the past, it reversed in the past. And then this was actually what he had suggested. This was verified subsequently by other workers like Mercanton and Matuyama, who actually confirmed these two observations and said that, yes, the Earth's magnetic field has been reversing several times through the geologic past. Now, what this meant is that based on this, and if you could actually date these basaltic rocks, you can actually set up a paleomagnetic time scale. And you can actually have this paleomagnetic scale, which would have normal periods and reverse periods. So there was nothing in between. The Earth's magnetic field was either oriented the way it is today, or it was just almost the reverse of what it is today. So there was nothing in between, nowhere when the Earth's poles were somewhere randomly in between. So all the time the Earth has behaved like a dipole, but it's either got a polarity in one direction the way it is now, or precisely the opposite. So this was something that was known since the 1920, confirmed since the end of the 1920s. After that, however, when people began looking at the ocean floor, magnetometers that were being carried along the ocean floor, they began to realize that it was known by that time, of course, that the magnetic field switches over time. But what they understood is across the ridges, when a material rises up through the mid-oceanic ridges, it cools. Obviously, the material, the basalt that is forming at that particular time, it would be aligned in accordance with the Earth's present day field. And that's because magnetite itself, which is there in the basalt, right, it aligns with the field when it cools. This is as clearly as that, the magnetite clearly aligns with the prevailing field of the Earth. Now, Vine and Matthews in 1963 and F.W. Morley, now he was a Canadian geophysicist. The unfortunate thing is that he actually also noticed that this reversals in the Earth's magnetic field, I think he observed it in the Western Pacific, but when he observed it, he tried to publish it. He sent it to Nature, he sent it to the Journal of Geophysical Research. Both journals actually rejected it, saying that it was too speculative. Luckily for Vine and Matthews, their 1963 paper, I think it was in Nature, was actually accepted. And what they noticed actually was that it's not just the fact that you had about the mid-oceanic ridges, there was a symmetrical pattern. You had patterns of basalts which were parallel to the ridges, which were aligned in accordance with the present day field of the Earth, and then next to it you had another part which was precisely arranged in an opposite manner. And in fact, the whole of the ocean floor, you had these stripes of normal and reversely polarized magnetic fields on the ocean floor. These were basalts. Now, when the basalts were dated, when you managed to date, it's very difficult to directly date basalts on the ocean floor, but where they could, they actually found that they were at similar distance, edge, if you were similar distance away from the ridge. Now, what does this actually mean? And if you look at it pictorially, so we can represent it like this. So what you have is, suppose this is the crest of the mid-oceanic ridge, and this is the basalt that is erupting today. This is the black part, and this black part is the part which is normally polarized with respect to the present day field of the Earth. Then the white parts, the little white lines here, are the parts where the field is reversed. It was reverse polarity. And then as you move further away, again you have these little bands of normal polarity, and then again it's reversed in here. So what you have is what we call positive and negative polarity, because when you measure the magnetic field, it's measured in terms of milligals. So with respect to the field, at any particular latitude you expect a particular strength of the field. At that particular part, the local magnetization of the rock, that gives you the anomaly. If the rock is aligned in accordance with the present day field, you will get a positive magnetic anomaly. If it's aligned in a direction that is opposite to the present day field, you would get a negative magnetic anomaly. So there were two things that were observed. One is that you had this switching between normal and reverse, and the second thing that was seen is that the normal and reverse was symmetric across the axis of the ridge. So if you draw a mirror plane here, you'll see that this part is the exact image of the other. So they were completely mirror images. Now this mirror image part is very, very important. It's absolutely vital for us, because this mirror imaging, right, is what is telling us that the age of, say, a point here, which is at distance x on this side from the ridge, would be exactly the same as another distant part that is x at this side from the ridge. So this distance on either side, right, would be exactly the same, and the ages would be exactly the same, and the patterns that you say, so whatever is the discrimination that you see is simply because of my drawing, right, but the errors that are there, I mean, they would be exactly parallel on either side. So it will be exactly the mirror image. And if you look at it, it looks like a beautiful zebra stripes, which is why they're called magnetic stripes on the ocean floor. So the word magnetic stripes, right, has to do with seafloor, right, being symmetric, showing symmetric anomalies on either side of the mid-oceanic ridge. So, if you go a little further now, it means that from this part then, if you have magma coming in, erupting out, right, and then you get this normal part, right, it splits to the side across, and then you get a completely symmetric pattern on either side. So the Earth's the basalts that are being erupted at the ridge today, they split apart, they rift, they move apart. As they are erupting, I mean, as soon as they solidify and as they cool, they acquire magnetization in accordance with the present day field. When the Earth's magnetic field reverses, so the basalts erupting at that time would be aligned in accordance with the Earth's magnetic field at that particular time, which we are now measuring as a negative magnetic anomaly. So this way, you get these symmetric patterns of anomalies across the axis of the mid-oceanic ridge. So the beauty of this particular observation was that this was the proof of seafloor spreading. So you could observe that this was the proof that they were looking for. Seafloor spreading up to that time was a hypothesis. This actually proved that you had seafloor spreading at the mid-oceanic ridges. Now, we come back to Hess's question then. Seafloor was being produced, he had nothing to prove that. The magnetic anomalies on the seafloor that Vine and Matthews and Morley had discovered actually proved that the seafloor itself, right, was being produced. We know now that the seafloor was spreading, but where is it being consumed? Well, Hess had suggested that it was being consumed at ocean trenches. So the ocean trenches were the most likely parts, but to him this was a guess. He just thought that it was going down, so that's why they were, that was the part that was most likely the place that it was being consumed. Now, to look at this, we can actually take a look at this part of the part again. So the mid-oceanic ridges are here, right? These are all the mid-oceanic ridges, and the parts which Hess suspected were the places where the ocean floor was being consumed were actually the trenches which are here now. So the trenches, so I am drawing them very approximately. So all of these are trenches. So these are the parts where Hess was saying that ocean floor was being consumed. So all of these parts were ocean trenches here, right? So all of this are ocean trenches. So these trenches in this particular region, the trenches that you see along the western coast of South America, much of North America also here. So you have trenches extending up to about here. So all of these together tell you that there are many places on the Earth's surface, right, where the ocean floor is actually being consumed. Now, how do we know that? Now, this is again, I've just used Murray Tharp's brilliant map to show this. But how do we know? This is just the topography. We know that these coincide with the signs, the regions of major earthquakes. So this is where your trenches are, and as you can see, the earthquakes coincide with the trenches exactly as we saw or discussed in the last class. Right? So all of these parts, even passing through the Andaman Islands. So if you're wondering, right, why you had this large tsunami at Banda Aceh in 2004, you know that these actually lie on ocean trenches. So these have been responsible for it. And in fact, most of the ocean trenches have the largest intermediate and deep focus earthquakes all along here, right? You have to leave out a little bit part here, right? So just leave out that part, and then the rest of it is some of it is trench, right? Now, as you go a little bit further then, the proof of subduction. So subduction had been proposed. What was subduction? It's the sinking, the downwelling of the crust into the mantle that had been proposed first by Wenning Menes, right? Revived as an idea by Hess. This was then actually verified by two people independently of each other. The first person to do that was a Japanese, and he was working, which was very natural because Japan is the place which is most closely associated with ocean trenches. So this person called Wadati in 1928, he discovered intermediate focus earthquakes that these were associated with the Japan trench. Okay, and then an American seismologist, his name was Hugo Benioff, he discovered similar earthquakes, right, both intermediate deep focus earthquakes. These were associated with the Kermadec Tonga and the South American trench. So deep focus earthquakes, right, most of the mid-oceanic ridges, for example, are associated with shallow focus, sometimes intermediate focus, but most mid-oceanic ridges are associated with shallow focus earthquakes. The trenches are the locations which are associated with shallow, intermediate as well as deep focus earthquakes. So it means then that most major earthquakes on earth are actually associated with the trenches. So Benioff then found that if you actually plotted the foci of the earthquake, focus of an earthquake is the point from which the earthquake originates. If you plotted the foci of the earthquakes in both of the trenches that he had studied, Kermadec, Tonga and South American Trench, the earthquake foci fell on a plane that was dipping at approximately 45 degrees from the trenches. So it meant then both these observations, right, what it meant is both Wadati and Benioff, what they managed to demonstrate is that the earthquake sources become deeper as you move away from the trench at a subduction zone. So that means that's why it's got a dip of 45 degrees, and this inclined array, which I'll show you next, of earthquake sources, that this indicates a position at the top of the subducting slab. So diagrammatically now, this is what you can see. So this is a place where there is downwelling. So this part is a part where there is downwelling of material from the surface. So as it goes down, right, so you have earthquakes starting from here right down. So if you consider these to be deep, right, it keeps on going down to a depth of around 700 kilometers. So from 0 to 70 you will have shallow focus earthquakes, from 70 to 300 you will have intermediate focus earthquakes, 300 to 700 as deep focus earthquakes, and all types of earthquakes are associated with these. When you plot these foci, you can actually plot a best fit great plane, a plane, an imaginary plane, which is a best fit plane which contains all these foci. And this particular plane is what is referred to as the Wadati-Benioff zone. Now, this is an imaginary plane, so you can actually fit something which contains all these earthquake foci. But why do you get this? Why does it happen? And how can we interpret this as something that actually supports subduction? Well, it's simply, you see, the earthquakes happen when you have a cooler, very rigid material that is sinking into the mantle. Now, as it sinks in, so suppose this material goes in like this. So as it goes in, right, so this material would fracture. There are stresses created. So you're pushing something in, there would be stresses. Now, as these stresses happen, so these parts will fracture. So the fracturing and failing of the upper surface of this descending slab, the shock waves would be transmitted, right, and that is what would result or cause earthquakes at trenches. Now, these earthquakes at trenches, now they can happen at this part, they can happen in this part, they can happen even deeper. So that is why you can get shallow, intermediate and deep focus earthquakes also all associated with the trench, because the upper surface of this descending slab we must be able to trace that. Now, the deepest earthquakes we see are around 700 kilometers, around 660 to 700 kilometers. This means that this subducting slab we've talked about, it must be sinking to at least these depths, because unless it sinks to that depth, shock waves cannot be transmitted up to the surface from there. So shock waves are actually transmitted along the cool and rigid material. That's how we know that there is failure up to that point. So you can actually trace, the earthquakes serve to help us trace the slab up to a depth of 700 kilometers right from the surface, which means that the ocean floor, we finally have proof that the ocean floor that was created at the ridges, it is actually consumed itself at the trenches. So therefore, we have a complete picture of that supports what Hess was trying to say. And we can then bring all of this together, right, to conclude Hess's model. So Harry Hess, he observed that there were fossils on the ocean floor. These were at most 180 million years old, and the sediment thickness that you observed on the ocean floor, it was not compatible with 4 billion years of sedimentation. He thought that the new ocean floor was created at the ridges, and then the old ocean floor, right, finally when it became older as it moved away from the ridges, and it became consumed at the trenches when it was old. Now, the Earth's magnetic field, we know independently, it has undergone periodic reversals through time. And because of this, the magnetization of the ocean floor basalts, it reveals where magnetic anomalies exist on the ocean floor, right. And these magnetic anomalies that we detect, we know that they are symmetric about the mid-oceanic ridges. Now, this supported Hess's model of seafloor spreading. Finally, of course, the Wadati-Benioff zone, which is formed by the foci of earthquakes associated with the ocean trenches, this proves that the old ocean floor is being consumed at trenches, and therefore we can keep the surface area of the Earth constant. So we now have a model, right, which moves on from continental drift to saying how dynamic the seafloor is. Created at the ridges, consumed at the trenches. So we have a very, very dynamic seafloor. We have evidence in the form of seafloor magnetic anomalies. We have evidence in the form of the Benioff zone. So all of this means we know a lot about the seafloor now. But how does this link up with continental drift? Well, to do this, you'll have to wait till the next lecture, and then we can discuss all of these in the context of all the people who've contributed, whose works have contributed to our understanding. They're referenced here, and then it's a huge list, and it's actually a bigger list. I've just used the ones that I've used to actually picturize this. We wait till the next time. Thank you.